Okay guys, so today we're going to learn about binomial expansion, and this is going to go over a few videos actually. And I suppose the first thing to ask is, well, what is binomial expansion and what's the point of it? And I'm going to answer that by sort of showing us the origins and the process of binomial expansion, and it's just going to become obvious what I'm doing in one. Okay? So let's start with this a plus b to the power of 0. Well, anything to the power of 0 is 1, right? Now let's have a plus b to the power of 1. So I reckon this is 1a plus 1b, yeah? Now let's do a plus b squared. Oh, now I've got to start expanding brackets, right? But I reckon I can do this in my head. 1a squared plus 2ab plus 1b squared, isn't it? Okay. Now what about a plus b cubed? Oh. Now I've got to expand loads of stuff. So let's do it. This is a plus b times a plus b times a plus b. This whole thing is going to be a plus b times a squared plus 2ab plus b squared. It's just going to go on forever, isn't it? Plus ab squared plus a squared b plus 2ab squared plus b cubed. Simplify that up and I get a cubed plus 3a squared b plus 3ab squared plus b cubed. So now I can whack that in here. So that's 1a cubed, isn't it? Plus 3a squared b plus 3ab squared plus 1b cubed. Okay, I think we agree that that took a while. Okay, so if I rub this out and then I ask you to do the same for a plus b to the 4, you're going to groan and groan and groan. Okay, because that's a lot of work. This is the point of binomial expansion. To remove this work, we need some kind of formula, some kind of method to make this so much easier. And this is where we can see what's called Pascal's triangle coming in. You see there's a pattern forming here, isn't there? Okay? As I go along the terms, what's happening to my a and b each time? Well, a to the power of 1, b to the power of 1, okay. Now I look here. I've got a squared, so it starts off with this number squared here, and it must be times b to the 0, because b to the 0 is 1, isn't it? And here I've got 2ab, so my power here is reduced by 1, and I've got b to the 1. And here my a is a to the power 0, because that's 1, and here I've got b to the power plus 1. So in total, each time, I've got this power up here, isn't it? 2 plus 0, 1 plus 1, 2, 0 plus 2, right? Gives me 2. And also these coefficients, so the coefficient means the number next to the variable, okay? So the coefficient of a squared here is 1, the coefficient of ab is 2, okay? You can see that in Pascal's triangle, what we have in terms of these coefficients is 1, 1, 1, 1, 2, 1. So there's always 1s on the outsides, okay? And then the middle between two numbers are added together. So 1 on the outside for the next row. 1 plus 2 is 3, 2 plus 1 is 3, 1 on the outside, and I can keep doing this 4, 6, 4, 1, okay, for every order of x. And this is what I can do then, as I get onto my a plus b to the 4, I can immediately write out, well, this must be 1a to the 4, b to the 0, plus 1 and 3 is 4, a to the power reduces by 1 for a, so it must go to 3, b to the 1, 3 plus 3 is 6, so I get 6, a to the b, a squared, b squared, 3 and a 1, plus 4, a to the 1, b to the cubed, plus finally the 1 on the outside, so 1b to the 4. Do you see, I can just keep moving this pattern along, and this is called Pascal's triangle. Okay, I'm using the Pascal's triangle method in terms of the coefficients, and then just reducing the powers by 1 each time, and all of the powers always add up to the number, this power n here, okay? So this first method, Pascal's triangle, this is your fallback method. This is the method you're going to use if you don't remember what you're going to learn in a bit, which is the actual binomial expansion formula, okay? With Pascal's triangle, you could pretty much solve anything. So you could solve the expansion of, say it asks you to expand 1 plus x to the power of 10, or 2 minus a half x to the power of 20, just by subbing in, well, in this case a equals 1 and b equals x, and in this case a equals 2 and b equals minus a half x, doesn't it? Okay? But the thing about Pascal's triangle is, if I asked you to find this 10 term, and especially this 20th expansion row, it's going to take you forever to write all this down. It's going to take you a long time, it's very tiresome, and you could easily make mistakes. Okay? The other point is that if I asked you to say, well, I want to know what the coefficient of x to the 30 is in the expansion 2 minus x to the power of 40. Okay, I want to know what's the missing coefficient here. Are you really going to want to write out all this Pascal's triangle in order to find that? No, we need something more efficient, more concrete, and this is again where binomial expansion formula comes in. Okay, so that's what we're going to learn about on the next slide. Okay, I could just give you the binomial expansion formula, but that's too easy. We need to understand where this binomial expansion formula comes from in order for us to use it. And also in the C2 exam, you could be asked on elements of the construction of the binomial formula. So that's why I want to start you from base, okay? So what we're going to learn about is this theory of combinations. So what we're talking about is this, what's called n choose r. N choose r. So this is looking at the coefficients next to a number. So if I had example 1 plus x to the power of 6, and the question is asking me what's the coefficient of, so the coefficient, this, whatever this number is, of x to the 5, okay? My n is the power here. My r is the power I'm looking for here, okay? So 5. So we need to know first off what this n choose r is. So n choose r equals n factorial over n minus r factorial times r factorial. So of course, first you're going to be asking me, well, what is factorial anyway? Okay, so this exclamation mark here is called factorial. So if I had 5 factorial, all this means is 5 times 4 times 3 times 2 times 1. If I had 10 factorial, 10 times 9 times 8 times 7 times 6 times 5, times 4 times 3 times 2 times 1. Okay, do you see? That's what the factorial means. And also you need to know that by definition, which is, I'm not going to prove here, it's beyond our scope, by definition 0 factorial is 1, and 1 factorial is 1. So 1 and 0 factorial are both the same 1. Okay, so if I'm looking at this n factorial will be n times n minus 1 times n minus 2 times n minus 3, and it goes on, doesn't it? Okay, so that's what factorial means. Now the reason I'm going to use this is this way. Okay, let's imagine I've got 5 different objects, A, B, C, D and E. I want to know how many different combinations I can have. If I take two of these objects, how many different combinations can I have? And I could do this using pairing, couldn't I? So I could have A and B, I could have A and C, I can have A and D, I can have A and E. I could then have B and C, B and D, B and E, couldn't I? Or I could have C and D, I could have C and E. Or I could have D and E. And there are the only combinations, aren't there? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different combinations, okay? What happens if I had 1,000 different unique numbers and letters and stuff, and I wanted to find, so if I had them scattered all over the place and I wanted to find how many combinations there were if I took two different things. Now that would take me forever to pair that up, wouldn't it? And this is where the theory of combinations comes in, okay? So this is where n choose r comes in. So if I have 1, 2, 3, 1,000 choose 2, because r is the number of units I want to take away, and 1,000 is how many are available. Okay, if I type that into a calculator, there is a button. So I would type in 1,000, and I would put shift and then the NCR button, and then I'd write 2. I should get the answer as 499,500 different combinations. Okay, so that's staggering. There's no way you would have done that, but this formula, what the calculator is doing is putting it into our n choose r formula. So this is 1,000 factorial divided by 1,000 minus r is 2 factorial, all times 2 factorial, and that would give us our 499,500 answer. Now the reason this is used in binomial is because you can imagine if I had a plus b to the 4, let's say, this is a plus b times a plus b times a plus b. Okay? So if I'm looking at theories of combinations, I could say, well, for a cubed, b, because from Pascal's triangle I know that these two powers added together must equal this, don't I? Yeah? I want to try and find the coefficient here. And what I'm doing is, this theory of combination is, I'm saying, okay, how many ways can I make a cubed? So I could start with this one, couldn't I? I got this times this gives me a cubed, or I could do this times this gives me a cubed, or I could do this times this gives me a cubed, yeah? So I can use my theory of combinations, my n choose r. My n is 4, choose 3. Type that into a calculator, all we can use is 4 factorial divided by 4 minus 3 factorial times 1 factorial. So that would give us 4c3 gives us 4. So actually the coefficient would be 4 in this case. So remember, this is all leading up to building up the binomial expansion formula, which we'll do in the next video, okay? In the next slide I'm just going to do some more examples of these factorial problems. So a couple of things. N choose r can be written in vector form or column matrix form. So nr, like so, okay? So if I had 7 and 1, this is the same as saying 7 choose 1, which from our formula is 7 factorial over 7 minus 1 factorial times 1 factorial. So let's not put this in a calculator this time, let's work this out manually. So this is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, this is 6 factorial, isn't it? So this is 6 times 5 times 4 times 3 times 2 times 1, and 1 factorial is obviously just times 1. So do you see that actually this whole thing cancels, doesn't it? So my answer would be 7. And if I type that in the calculator, that's exactly what I would get.